Good morning. Today we are going to start our next chapter, the fundamental theorems and basic methods. Okay, so just to recall what we have studied in our previous classes. Here we have discussed what you mean by a linear space. Linear space, you know the definition of linear space over the field of R and a complex number C, the definition of vector spaces. Okay, also we know what is the dimension of a vector spaces and what do you mean by a normed spaces and what do you mean by a complete linear space, and we call a complete linear space as a complete normed space as a Banach space. Now linear functional, the definition of a linear functional, and the set of all linear functional is denoted like this, and the set of all bounded linear functional denoted as x star, and we define norm of f as supremum of x not equal to 0 mod f of x by norm of x. Okay, also we have a result dual space of a normed space is also a Banach space. Now, in general, if L is the space of all bounded linear maps from X to Y, then we have defined norm of A as, if A is a bounded linear map from X to Y, then we define norm A as supremum of X not equal to 0, norm of AX by norm of X. Okay, like that we have uh, discussed Banach space also. Okay, and in this section we are continuing the result. We are discussing main theorems related to Banach space. We'll start with the next sections 9.1, which is discussing about some basic results like definition of a metric, like that. Okay, now what do you mean by a metric? Okay, in a set M, we define a distance. Okay, distance as a non-negative function rho of xy for x comma y belongs to M. We are defining a function rho of xy or distance function, or we call it as a metric if it satisfies some following conditions. Now what are the conditions? Rho of xy equal to 0 if and only if x equal to y, rho of xy equal to rho of yx, rho of x plus y is greater than or equal to x plus rho of xy plus rho of yz is greater than or equal to rho of xz. So first condition is rho of xy equal to 0 if and only if x equal to y. Second condition, rho of xy equal to rho of yx. And third condition, actually triangle inequality. Rho of xz is less than or equal to rho of xy plus rho of yz. Okay. This condition satisfies, then we call rho is a metric. A set M with a metric is called metric rho is called a metric space. A set. Now we are going to discuss the definition of a complete metric space. A metric space is said to be complete if for any sequence xn subset of M such that rho xn xm tends to 0 as n comma n tends to infinity, there exists a limit x belongs to M such there exists a limit x belongs to M. That means the limit of that sequence must be in M. That is limit n tends to infinity, rho xn x must be equal to 0. Okay, this is actually a definition of a Cauchy sequence. In general, we see a space is said to be complete. Every Cauchy sequence is convergent. Same meaning. Okay, so rho x and whenever there is a sequence satisfying this condition, then the limit must be in yeah. For a subset of M, we denote A0 for set of interior points, A bar for the closure, and AC the complement of A. Okay. Now listen carefully. We are moving to another definition. The definition of a novel dense set. So a subset of M is said to be novel dense if the closure A closure does not contain any interior points. If A closure does not contain any interior points, then that set is said to be novel dense. Okay. So, if a set A is nowhere dense, what's the meaning of that? Then for any open ball B subset of M, there exists an open ball B1 contained B such that B1 intersection A must be non-empty. B1 intersection A must be non-empty. Okay. So what is the meaning of that actually? A is said to be nowhere dense if A closure does not contain any interior point. A closure means what? A closure means what? The set of all, the set of all A and the union of its limit points. Okay. So if that does not contain any interior point, then that set is said to be nowhere dense. Now we are moving to this result. Now, what is the result? If A is nowhere dense, then for any open ball B, there exists an open ball B1 such that B1 intersection A equal to empty. Then there exists a open ball B which does not contain any points of A. Note if B is an open ball, then what is B intersection A closure complement? Which is equal to B minus A closure. This is non-empty. That is B minus A closure is non-empty. Okay. So, what is the meaning of that? B1, that is B1. Okay. Okay. Now we are moving to the proof. Suppose B intersection A closure complement is not equal to empty. What happens? That means B minus A closure is empty. That is B intersection A complement is empty. That means B is completely contained in A closure. If B we have removed from A complement, that's A complement A bar is equal to empty implies B is completely contained in A bar. Okay. Now what is B is an open ball. Okay. Therefore A bar contains interior points. B is open ball, that means A bar contains interior points, which is a contradiction because we have taken the given set A is a nowhere dense set. Nowhere dense set means that does not contain any interior point. If B is an open ball, then all the points are interior points. That means A closure contains interior point, which is a contradiction. Therefore, B minus A bar is not equal to empty. Now what we have to prove? We have to prove if A is nowhere dense, then for any open ball B subset of M, there exists an open ball B1 subset of M such that B1 intersection A equal to empty. That is what we have to prove. Note that B minus A complement is open and there exists a open ball B1 contained in B minus A bar. Okay, because B minus A complement, B minus, we have B minus A complement is not equal to empty. Okay, that means B minus, B is an open ball, therefore B minus A complement is again open ball. That means there exists an open ball B1 which is contained in B minus A complement. B1 is contained in B minus A bar implies clearly B1 intersection A is equal to empty. Thus we get the result. Once again, I will repeat. Suppose What we have to prove? We have to prove if A is no dense, then for any open ball B contained in M, there exists an open ball B1 contained in B such that this condition holds. Okay. Now, if B is any open ball, then clearly B minus A closure must be non-empty. This is the proof of that one. Okay. So suppose this is equal to empty, that means B intersection A complement equal to empty. That means B is completely contained in A complement. B is an open ball. A bar contains interior points, which is a contradiction. Therefore, B minus A bar is clearly not equal to empty. So this is an open set. Okay, so B minus A bar is an open set, means there exists an open ball B1 contained in B minus A bar. Okay, so this for this ball B1, clearly B1 is completely contained in B minus A bar. That means B1, no points of B1. No, all points of B1 is completely contained in B minus A bar. That means no points of B1 is contained in A bar. That is B1 intersection, actually B1 intersection A bar is also empty. That is B1 intersection A is also equal to empty. Hence the result. Now for the converse part, let A be a set in a matrix space M. Assume that for any ball, open ball B subset of M, there exists an open ball B1 subset of B such that B1 intersection A equal to empty. Then we have to prove A is nowhere dense. If possible, assume that A is not nowhere dense. That means A closure has an interior point. Let U be an open ball with a center at x0. Let x0 be the interior point and U be an open ball with a center at x0 such that U is completely contained in A closure. Then for any open ball, we have B1 contained in U such that B1 intersection A is not equal to for this. Okay, B1 contained in U, we have B1 intersection A is not equal to empty because U is completely contained in A closure. Okay, so for this any open ball B contained in U, we have B1 intersection A is not equal to empty. Okay, because for this we have assumed that. Okay, we have assumed that this is nowhere, assumed that A were not nowhere dense. That means this has an interior point. Therefore, this has an open ball contained in. Okay, so for any, this is contained in a closure. So any open ball B, but we get clearly B1 intersection A is not equal to empty because B1 is completely contained in A closure. Okay, therefore B1 intersection A is not equal to empty, which is a contradiction. Therefore, A is nowhere dense. Okay, now moving to next definition. A subset of M is said to be of first category if A is a union of countable many sets. That is A equal to union IBI, where BIs are nowhere dense for all I. If A is a union of nowhere dense sets, then A is said to be a of first category. A set C which is not of first category is said to be of second category. A set C which is not of first category is called of second category. Now we are going to prove bare category theorem. This is very important. Every complete matrix space M is of second category. What is a first category? If A is said to be a first category, if A is a union of countably many nowhere dense. Okay. So A is of M is of second category means M is not the union of nowhere dense sets. Okay. So we have to prove M is a set of second category. For this, we assume that M is not of second category. That is, M is of first category. That is, M is equal to union N is equal to 1 to infinity An, where Ans are nowhere dense. Now, we are choosing let B naught is equal to dx naught 1, be a closed board with radius 1 and the center at x0. Okay, clear? Now what about A1? A1 is a Noether set. Okay. Therefore, what happens? There exists an epsilon 1 greater than 0 and a ball B1 which is completely contained dx1 epsilon 1 such that B1 contained in B0 and B1 intersection A1 is equal to empty. Why? This given that A1 is a Noether set. Okay, what is the meaning of a Noether set? Once again, I am going to the definition. A set A is said to be of Noether if its closure does not contain any interior points. Also, we have this result. If A is a Noether then for any open ball B contained in M. If A is Noether then any open ball B contained in M. There exists an open ball B1 such that B1 contained in B and B1 intersection A is equal to empty. We have this result and we are applying this result. Okay. So for we have A1 and we for B we have D of x naught 1. Okay. So that means there exists A for B we have this B1 subset of B such as B1 intersection A equal to empty. Okay. So once again. So here we are taking B naught dx is a closed ball with radius. Okay. And since A1 is Noether set, the given epsilon greater than 0, there exists a ball B1. Even though this is closed or open, no problem. Okay, there exists a ball B1. B1 must be open such that x1 epsilon 1 such that B1 is completely contained in B0 and B1 intersection A1 is equal to empty. Okay. So we can choose B1 to be closed. Okay, we can choose closed and epsilon 1 must be less than 1 by 2. Okay. Now, since A2 is Noether there exists a closed ball B2 equal to dx2 epsilon 2 with radius 0 less than epsilon 2 which is less than 1 by 3. Okay, such that B2 contained in B1 and B2 intersection A2 is not equal to empty because here A2 is Noether. So, given any ball for this ball, okay, B1, there exists a subset, okay, B2 such that B2 contained in B1 and this condition. Continuing like this, we get a sequence of closed balls Bn is equal to Bxn epsilon n and epsilon n less than 1 by n plus 1. Okay, Bn plus 1 contained in Bn and Bn intersection An is equal to empty. Now we claim that Xn is a Cauchy sequence. For m greater than n, where is Xm? Xm is in Bn because Bm is Bn plus 1 contained in Bm. Okay. So Xm is contained in Bm is contained in Bn. Actually Xm is contained in Bm. Bm is for m greater than n, Bm is contained in Bn. Therefore, rho xm xn is strictly less than epsilon n because xm is contained in Bm means that radius rho xm and the center of Bn is xn. Clearly less than epsilon n and this is less than 1 by n plus 1 that means tends to 0 as n tends to infinity. Therefore, xn is a Cauchy sequence. Since M is a complete space, this Cauchy sequence converges. That means there exists a y0 belongs to M such that y0 is equal to limit n tends to infinity xn. Now x1, x2, etc. belongs to B1. B1 is closed. Therefore, limit xn is also belongs to B1. Therefore, y0 also belongs to B1. As B1 intersection A1 is equal to empty, y0 not belongs to A1. Similarly, x2, x3, x4, etc. belongs to B2. Limit xn also belongs to B2. Limit of this sequence is y0. That belongs to B2. But y0 not belongs to A2. Finally, we get, proceeding like this, we get y0 belongs to Bn and y0 not belongs to A. So y naught is not belongs to union n equal to 1 to infinity a because y naught not belongs to a1, a2, a3 like. So y naught not belongs to a. But y naught is the limit of the sequence and that must be an element of m. Therefore, y naught not here belongs to m is a contradiction. Because as m is complete, limit also must belongs to m. So our assumption is wrong. M is of second category. So this contradiction occurs as we assume that m is of first category. That is wrong. Therefore, m is of second category. Okay. So let's revise what we have discussed in our today's class. We have discussed one definition, that is a definition of a metric. Okay. Then complete metric, then no dense set, then one property, a set A is no dense, then for any open ball B subset of M, there exists an open ball B1 contained in B such that B1 intersection A is equal to empty. Okay. Then we have discussed bare category theorem and there is one result. Set A is said to be a first category if A is a union of countably many sets, countably many no dense sets. Okay. Okay, now the result is bare category theorem is every complete matrix space M is of second category. So hope everything is clear.